All right, class. Today, I'd like to go over Cramer's rule, Cramer's rule. I'm sure there's a specific way to pronounce this. And it is a different or alternative way of solving a system of linear equations. So it involves taking determinants. And so if we have a matrix system like so matrix A times a vector of x values equals some other vector of b values. So then we have it, so as long as A has an inverse, or as long as the determinant of A is not equal to 0, then this system here, we can write that it has, some solution that looks like so. So x1, x2, all the way down to xn, all right, where each one of these, so let's index it by I, so where xi is going to be equal to the determinant of matrix B I over the determinant of matrix A. Okay. So, for example, if we want to know what the solution to x2 is, we would have that x2 is equal to the determinant of matrix B2 over the determinant of matrix A, where x2 is going to be A, so x2, where B2 is equivalent, let me put the arrows up here because these are matrices, where B2 is equivalent to matrix A with column I, or with column 2, replaced by vector B. Okay, so we're going to take vector B, which again, this is just going to be some column vector of B values. They're constants, right, all the way down to Bn. And we're going to move it and replace columns in matrix A. All right, so let's do a quick example of one of the matrices that we've been working with. So let's say we have the following system here. It's 2, 4, 5, 0, 3, 0, and 1, 0, 1. So that's matrix A. And then we have times vector x, so x1, x2, x3 is equal to vector B, which again, 0, 5, negative 4. We've worked with this system before, so we know what the answers to. We know what the solution for x1, x2, and x3 are already. We just want to use Cramer's rule to solve for that. So hypothetically here we have, using this rule here, then we know that this implies value x2. So this value here is going to be equal to, so again, it's going to be column A with it's going to be matrix A with column 2. So this column here, so this column here replaced with vector B. That's going to be matrix B2. Okay, so it's going to be the following determinant. So we're going to have 2, 0, 1. Now we're not going to have 4, 3, 0. We're actually going to place column 2 with B. So it's going to be 0, 5, negative 4. And then 5, 0, 1. So it's going to be that determinant divided by our determinant of A, which again is 2, 4, 5, 0, 3, 0, 1, 0, 1. All right. I think we already have done the determinant for this. If I remember correctly, it's -9, but we can always double check. Let's just expand. Why don't we expand across the bottom row? So this right here will be equal to 1 times the determinant of, again, we get rid of this column and that row, and it's 5, 4, 5, 3, 0, right? Minus 0, so 0 times 0 is 0, and then plus 1 times the determinant of, we're going to get rid of this column and this row, and it's going to be 2, 4, 0, 3. Okay, and that just equals 0 minus 15, and then that is just 6 minus 0, so plus 6, and that equals -9, as we expected. Now let's do this determinant here, and just for ease, let's just expand across this row here because there's 2 zeros there. And so that's going to be, it's going to be, let's see, this entry here is row 2, column 1, so that's an odd entry, and that means it's going to be a negative, but it's 0. And then this is row 2, column 2, so that's 2 plus 2 is 4. That's a positive entry, so it's just going to be 5 times the resulting matrix where we get rid of the second row and the second column. So it's just 2, 5, and 1, and 1. So that's going to be equal to 5 times 2 minus 5. 2 minus 5 is -3. So that equals -15. Right? So we just take the ratio of these two. So that tells us that x2 is equal to -15 divided by -9, which can be simplified to 5/3, right? Which I believe is the answer that we got from earlier on when we did this using just the basic inverse, right? And now what I'd like to do is to actually take Cramer's rule or Cramer's rule and try to solve out the famous ISLM model that you all learned in Econ 202, or will learn in Econ 202 if you haven't taken it yet, but I think you've all taken 202 at this point. So we have an IS curve, which is just going to be S times Y plus A times R is equal to autonomous investment plus government expenditures. All right. And we have, so again, this is just going to be our demand correspondence here for this model. And then here, this is going to be the money market, so it's going to be M times Y minus H times R is going to be equal to the money supply, MS, minus the initial or autonomous supply of credit or money. And so what we have are two endogenous variables here. It's Y, or output, or demand, if you want to call it that, and the interest rate R. So we have to write this in a way where we put this into matrix form. Okay, so here you can see there's a Y here and there's an R there. There's a Y here and there's an R there, and there's this constant. So I'm thinking we can make we can make a matrix and then have vector Y and R, and then have this as, vector B. So this matrix system can be written as such, and we can double check this. It'll be S and A, and then M and negative H. And we're going to be multiplying that by this vector X, which is just Y and R. And it's going to be equal to this vector B, which is autonomous investment plus government expenditure, and then the money supply minus autonomous money, M naught. Okay, I believe that should check out. Okay, so now let's see if we can use Cramer's rule to solve, let's say, for Y. So if we're going to solve for Y, so Y is going to be equal to the determinant of this matrix here, but with the first column replaced by B. So it's going to look like this. We're going to have I naught plus G as the first entry, and then we're going to have A, and then we're going to have MS minus M naught, and then we're going to have negative H. And we're going to divide that by the determinant of S, A, M, negative H. Okay? And that's just going to be equal to, if you remember how to do the determinant of a 2 by 2, it's just the product of this minus the product of the opposite. So it's going to be, so I naught plus G times negative H minus A times MS minus M naught. All right. And we're going to divide that by the determinant of this matrix system down here. I'm sorry, this matrix here. So that's just negative S times H minus A times M. So there seems to be a lot of negatives here that I believe can be factored out. If we multiply the top and the bottom by -1, it turns everything positive. So that just becomes H times I naught plus G plus A times MS minus M naught. And it's going to be divided by SH plus AM. Okay, so that's, again, don't forget, this is equilibrium output. Put a star there to indicate that it's equilibrium output. Now let's solve for the equilibrium interest rate. So that's going to be equal to the determinant of this matrix here, but with the second row now replaced by column B. I'm sorry, vector B. So it's going to be S, and then we're going to have I naught plus G. And then down here we're going to have M, and that's going to be MS minus M naught. And we're going to divide again by the same determinant, S, A, M, negative H. And that's going to give us, just take the determinant, so it's S times MS minus M naught. minus M times I naught plus G. Sorry, I think this was supposed to be up here. Divided by the same thing, negative SH minus AM. Okay. So now if we multiply the top and the bottom by -1, what we get is M times I naught plus G minus S times the money supply minus the autonomous supply of money over SH plus AM. And again, that's equal to R star. All right. So those are our two equilibrium solutions to this here. Right. And, you know, this will allow us to make predictions about what's going to happen to the interest rate and what's going to happen to equilibrium output. So what do we think is going to happen, let's say, for example, if government expenditures increase? Right? We can do a comparative statics here and say, all right, well, if G increases, all right, and nothing else changes, then we should have R star increase by some proportion of M over SH plus AM. All right. So in this case, if G goes up, R star is going to increase as well. Should make sense. This is the classical result from your macro course of government expenditure crowding out private sector investment, raising the interest rate. In other words, usually when the government has to spend more money, it usually has to borrow more, so that puts pressure on the demand for financial capital. And if there's a higher demand for borrowing, that's going to push interest rates up. All right, what's going to happen to our output? So this is like a form of stimulus here. So if G goes up, you can see that output, Y star, is also going to increase as well. All right. So this will kind of be the classical result where, you know, if we've got a graph where we have Y here on the x-axis and R on the y-axis, we have our IS curve and our LM curve, and we have G increased. That's the same thing as a shift to the right of the IS curve. This is with G increasing, and you can see that you get, so this will be R star 1, Y star 1, and we end up with an increase in Y star to Y star 2, and an increase in R star to R star 2. Okay. You could do similar things. Let's say, for example, if the money supply increases, so if we do like an open market operation, and increase the supply of credit in the economy. So if MS increases, right, then you can see there's a negative here, and that means that interest rates are going to go down. So if MS goes up, we get that R star is going to decrease. Okay, makes sense. Greater supply of money in the money market, interest rates are going to fall. And then what happens to output? So if MS increases, output's going to increase as well. So that would be Y star increasing. Okay. That would be characterized with an ISLM model that looks like this. So we have our IS curve, LM curve, right? And this LM curve would shift to the right. So that would be LM with an increase in the money supply. And you could see that the equilibrium goes into that direction here. So this would be the first equilibrium allocation. And this now is the second equilibrium allocation after the increase in the money supply. All right, interest rates go down, output goes up. It's a basic monetary stimulus. So government stimulus results in higher rates of interest, the interest rate. Monetary stimulus usually results in lower interest rates and a higher level of output. All right. So again, this is Cramer's rule or Cramer's rule. Very, very useful in linear algebra, but especially useful when we're talking about economic systems that can be written in state space form or matrix form here. All right. This will be a classical example of what we're going to do a lot in the first part of this semester when we dig into our textbook, because we're going to be looking at dynamic systems that are going to be written in matrix form, and we want to sometimes solve out for the steady state values like this. We could use Cramer's rule. That's one of the ways we can solve those out. All right. Hopefully this helps, and maybe start taking a look at some of those exercises in the back of the notes, because I think at this point you can probably start doing them on your own. All right. Okay, next section is going to be on eigenvalues and eigenvectors. I'll probably post that video later on this week just to give you time to digest Cramer's rule. All right, till the next time.